The traditional network perimeter is dead. The assumption that you can build a hard shell with firewalls and DMZs and implicitly trust everything inside that shell that's obsolete? Cloud migration, remote work, and BYOD have completely dissolved the physical network boundary.
Precisely. If you're still relying on a trusted internal network where a user gets access simply because they're plugged into a specific Ethernet port or logged into a corporate VPN, you are operating on a legacy fallacy. That model simply does not work in a decentralized environment.
Today's deep dive is on zero trust architecture. We're specifically analyzing the NIST SP 800-207 standard. Our mission here is to move beyond the marketing buzzwords. We're going to break down the logical components, the protocol standards, and the implementation pillars necessary for a never trust, always verify environment.
Which is exactly what we need to cover in part 1, the philosophy and definitions.
This content is AI generated using deep research and verified sources. We're committed to accuracy over generic AI output. All right, let's start with the core definition. I always say zero trust in an engineering context. What are we actually building?
It's crucial to understand that zero trust is not product. You can't just buy it. It is a strategic framework. The core definition, according to NIST, is a model where no implicit trust is granted to assets or user accounts based solely on their physical or network location.
Because in the legacy model, trust was a function of location.
Exactly. In zero trust, we assume the network, even your local area network, is inherently hostile.
And this shift didn't happen in a vacuum. There were two specific historical catalysts that forced this architectural change. First was Google's Operation Aurora in 2009.
That was a pivotal moment for the industry. Aurora was a sophisticated state-sponsored attack that bypassed perimeter defenses and moved laterally to steal intellectual property. That failure led Google to develop BeyondCorp,
Which was really the first large-scale implementation of zero trust.
It was. It shifted the access control plane from the network perimeter directly to the individual user and device.
The second catalyst was the Snowden revelations in 2013. That led directly to the IETF publishing RFC 7258.
RFC 7258 is a critical document for network engineers. It explicitly declared that pervasive monitoring is an attack. It forced the engineering community to design protocols with the assumption that the network backbone itself, the actual wire, was being tapped.
It shifted the mindset from preventing access to encrypting and verifying everything, everywhere.
Right. Which brings us to the 3 philosophical pillars that guide operations in a zero trust environment. If you are architecting a system today, these are your hard requirements.
Pillar number 1, verify explicitly.
This means we authenticate and authorize based on all available data points. It's not just about a static password anymore. We look at identity, user location, device health, service classification.
And behavioral anomalies.
Yes. If any signal is out of baseline, like an impossible travel scenario or an outdated OS, we deny access.
Pillar number 2, use least privilege access.
This focuses entirely on limiting the blast radius. We implement just-in-time, or JIT, and just-enough access, JEA, principles.
Meaning users and services should only have access to the specific resources they need for the exact duration they need them.
Exactly. Permanent administrative access is an anti-pattern in this model.
And pillar number 3, assume breach.
This is the operational mindset. You must architect systems as if an attacker is already present on the network.
We stop focusing solely on ingress prevention.
And start focusing on minimizing lateral movement and exfiltration capabilities.
For those watching the video version, we have a graphic on screen comparing the architectures. On the left is the legacy perimeter, a flat network where internal traffic is largely uninhibited.
And on the right is the zero trust model. You can see the microperimeters drawn around individual resources. Every single connection is a new decision point.
Let's transition into the technical deep dive section. We'll start with subsection A, logical architecture as defined by NIST SP 800-207.
This is the blueprint. NIST clearly separates the control plane from the data plane. Let's look at the brain of the system, the policy decision point, or PDP.
The PDP is where the logic resides, and it's composed of 2 functional components, right?
Correct. First, the policy engine, the PE. The PE is the ultimate decision maker. It ingests inputs like identity, state, and enterprise policy rules. Then it outputs a Boolean decision, grant or deny.
So the policy engine makes the call. Who executes it?
That is the policy administrator, the PA. The PA takes the decision from the engine and executes it by generating the necessary tokens, keys, or credentials to allow the session to be established.
It communicates with the network infrastructure to set up the path. But the PDP only handles the logic in the control plane. The traffic still has to pass through a mechanism in the data plane.
Which brings us to the policy enforcement point, or PKey.
The gatekeeper.
Exactly. In a modern stack, this could be an API gateway, an identity-aware proxy, or a next-generation firewall. The PEP terminates the connection from the user or workload. It holds the traffic until the policy administrator signals allow this through.
And if the policy changes mid-session, say a device's health degrades because an EDR agent was disabled,
the PA instructs the PEP to terminate the connection immediately.
but the PEP cannot make these decisions without data. It needs context.
That context constitutes the policy information point, or PIP.
The PIP represents your ecosystem of data sources.
It includes your threat intelligence feeds, your device health logs from an MDM or EDR, your ID management system, and your data classification tags.
So the policy engine queries these PIPs. It asks, is this device patched, or is this IP address associated with a known botnet, before rendering a verdict.
Look at the flowchart diagram on screen. The subject connects to the PP. The PP queries the PDP. The PDP checks the PIPs, makes a decision, and instructs the PEP to open a microtunnel to the resource.
It creates a loop of continuous verification.
Exactly. It moves authorization from a static, one-time event to a dynamic, continuous process. To build this out effectively, you need to mature across specific functional areas.
Let's move to subsection B, the 7 pillars of maturity. This framework is derived from CISA and DoD maturity models. The first functional area is identity.
Identity is the new perimeter, but the focus here extends far beyond human users. We must scrutinize machine identities, bots, service accounts, and API keys.
Those are often the weak link because they lack the friction of MFA.
In a zero-trust model, machine authentication must be just as robust as human authentication.
Next is devices.
You cannot trust a request simply because the user credentials are valid. The device itself must be trusted. We require real-time inventory and health compliance.
Is the disk encrypted? Is the EDR agent active? Is the OS patch level compliant?
If the answer is no, the device is effectively invisible to the network resources.
Then we have network.
This is where we eliminate the flat network structure. We use microsegmentation and software-defined perimeters, or SDP.
The goal is to make resources dark.
Right. If a user is not authorized, they cannot even ping the server. The PEP drops packets before they reach the resource, preventing reconnaissance and port scanning entirely.
Fourth is data.
The crown jewels. Data requires strict classification and end-to-end encryption, both in transit and at rest.
Because even if an attacker bypasses network controls, the data itself should be unreadable without specific decryption keys.
Keys which are released only upon policy verification from the PDP.
Let's bundle the last 3. Visibility and analytics, and automation.
Visibility provides the feedback loop. We need centralized telemetry, ingesting logs from the identity provider, the EDR, and the network to detect anomalies.
And automation is the force multiplier.
If the system detects a compromised device via telemetry, an automated playbook should trigger to quarantine that device immediately at the PEP level. No human intervention required.
To make all these pillars interoperate, we rely on specific protocols. Let's hit subsection C, protocols and standards. What are the actual technologies enabling zero trust?
It starts with SAML 2.0. This remains the standard for enterprise single sign-on. It allows an identity provider to pass authorization credentials to a service provider via XML assertions.
It is established and robust for legacy enterprise applications. But for mobile applications and modern RESTful architectures, SAML is often too heavy.
Correct. That is where OIDC OpenMD Connect is utilized. Built on top of OAuth 2.0, OIDC uses JSON Web Tokens, or JWTs.
It is lightweight and optimized for mobile and single-page applications.
If you are building cloud-native apps today, OIDC is the preferred standard for identity assertion.
What about server-to-server communication, workload-to-workload security?
That is where mTLS mutual TLS is mandatory. In standard TLS, the client verifies the server certificate. In mTLS, the server also verifies the client certificate.
Both parties must prove their identity. It enforces mutual distrust.
If a rogue workload attempts to connect to a database without a valid certificate signed by the internal certificate authority, the connection is rejected during the handshake.
And finally, for the user authentication side, we have FIDO2 and WebAuthn.
This is the gold standard for phishing-resistant authentication. It utilizes public key cryptography to replace shared secrets, like passwords.
The private key never leaves the user's hardware device, such as a YubiKey or a platform authenticator.
Which mitigates credential harvesting attacks effectively.
That covers the architecture and the protocols. but theory must be applied. Let's move to the practical application section. We will analyze two major failure modes and how zero-trust principles would have mitigated them.
First is the SolarWinds supply chain attack.
The scenario. Attackers injected a backdoor, known as Sunyo into the build pipeline of the SolarWinds Orion platform.
The failure mode here was implicit trust. Organizations trusted the digitally signed software update. Once that compromised software was installed, it resided inside the perimeter.
Because network monitoring tools typically require broad access, the compromised server had the ability to move laterally and initiate connections to command and control domains.
Exactly.
So how does zero-trust architecture mitigate this? The malware was signed, it would pass the identity check.
It would pass identity, yes. However, it fails the least privilege and microsegmentation checks. In a zero-trust architecture, the SolarWinds server should only be allowed to communicate with the specific devices it manages on specific management ports.
It should not have the ability to initiate arbitrary outbound connections to the internet.
Or lateral connections to email servers. Microsegmentation would have blocked the lateral movement, and a default deny policy on the gateway would have blocked the C2 traffic.
Let's examine case study 2. Colonial pipeline. This ransomware attack disrupted fuel distribution across the U.S. East Coast.
This breach occurred via a single stolen password for a legacy VPN account. Crucially, the account did not have MFA enabled.
The failure mode here is the legacy VPN architecture itself.
Exactly. A VPN typically provides Layer 3 network access. Once the attacker authenticated with that stolen password, they established a tunnel into the corporate network.
From there, they could scan the network, move laterally, and locate the billing systems to deploy the ransomware.
If they had ZTNA Zero Trust network access in place, the outcome changes drastically.
First, the policy engine would likely deny the access request because it lacked MFA or originated from an anomalous location.
But assuming they bypassed authentication, ZTNA provides Layer 7 application access, not Layer 3 network access.
The attacker would have a tunnel to a specific application, not the entire network subnet.
They would be unable to see or route to the operational technology network or the billing servers.
We have a comparison table on screen summarizing this distinction. VPN provides Layer 3 access, one-time authentication, and a high blast radius.
ZTNA provides Layer 7 access, continuous authentication, and a minimal blast radius. It's a fundamental shift in risk exposure.
However, implementation is challenging. There are common pitfalls. The most significant barrier is legacy debt.
Mainframes, AS400 systems, and legacy proprietary applications do not support modern protocols like OIDC or mTLS. You cannot simply install a zero-trust agent on them.
The solution is often to wrap these applications in identity-aware proxies,
which adds architectural complexity but allows them to participate in the zero-trust ecosystem.
Another pitfall is policy complexity.
The administrative burden of defining granular rules for every user and resource can be overwhelming. If done manually, it leads to overprivileged accounts, where admins create wildcard rules just to maintain velocity.
You need a policy engine that handles logic dynamically based on tags and attributes, rather than static access control lists.
And finally, user friction. If device compliance checks are too aggressive, for example, blocking access due to a minor browser version mismatch, it impedes business operations.
Security teams must balance strict verification with workflow optimization to prevent users from seeking workarounds.
Absolutely.
Let's move to our closing. We want to provide you with concrete steps. Here are 3 action items you can execute this week. Item 1. Calculate your excessive privilege ratio.
Audit a sample of your user roles. Compare the permissions they technically hold against the permissions they have actually utilized in the last 30 to 60 days.
The delta between those two is your risk surface. Item 2. Audit MFA adoption.
Target 100% MFA coverage. This includes remote users, internal administrators, and cloud console access. If a resource allows single-factor authentication, it is a critical vulnerability.
Item 3. Review protocol usage.
Identify where legacy VPN concentrators are still primary access methods. Select one non-critical internal application and pilot replacing the VPN access with an application-specific ZTNA tunnel.
This serves as a proof of concept for the broader architecture transition. That brings us to the end of this deep dive.
If we connect this to the bigger picture, remember that the perimeter has not disappeared. It has moved. The new perimeter is identity and context.
If you found this technical session valuable, please subscribe for more engineering deep dives. We are interested in your experience. Drop a comment below regarding your specific challenges with micro-segmentation or legacy app integration.
Here is a final thought to explore on your own. How does quantum computing threaten the current PKI infrastructure that underpins mTLS? It's something to prepare for now. Until next time, verify explicitly.
And assume breach. Thanks for listening.